Welcome to today's NC-CAV Center of Excellence Transportation Center. Today we are delighted to have Mr. Mohammed Islam as the speaker. The title of his talk is on deep learning approaches for pedestrian detection for enhancing the safety of autonomous vehicles. Before we start today's, please allow me to talk a little bit about Mohammed Islam. He received his Bachelor of Science in Electrical and Electronic Engineering in 2009 from Bangladesh University of Engineering and Technology. In 2018, he joined the North Carolina State University to pursue his PhD degree. He is a member of Autonomous Cooperative Control of Emergency Systems Lab. He is also a member of NC-CAV Center. His research focuses on computer vision applications, vision drive-by-wire control of autonomous vehicles. And in particular, his research focuses on developing deep learning-based models for pedestrian detection. Before he starts, I would like to thank the sponsors of the project, Downtown Greensboro, Verizon, Real-Time Innovations, and of course the main sponsors of the project, which is North Carolina Department of Transportation and CDOT. With that, I'll pass it to Mashouk.
Thank you so much, Professor, for introducing me. Let me share my screen. I hope everyone can see my screen.
Yes, we can.
Right. So thank you, everyone. So as Professor Ali already mentioned, the topics that I'm going to talk today is deep learning approaches for pedestrian detection for enhancing safety of autonomous vehicles. So without any further ado, let's go to the outline of this presentation. So here is the outline of my presentation. First, I'll provide a brief introduction on pedestrian detection using different vision technique, followed by some problems and challenges using those vision techniques. Then I will discuss about our proposed methodologies to resolve those. That I'll show our experimental result that will basically support our proposed methodology and show the robustness of our method. Finally, I'll finish the presentation with a conclusion. So now let's see some incident that influence us to detect pedestrian robustly. We cited some example of failure cases of autonomous vehicle in detecting a pedestrian. On March 18, 2018, an Uber self-driving vehicle struck and killed 49-year-old woman. The system could not determine whether it was a pedestrian, vehicle, or bicycle. And one of the probable reasons behind the failure in detecting this person is the lady's body was partially occluded and background was complex due to the bicycle and low light environment. And another incident with Tesla self-driving car on April 2021, which causes death of 2 people. So this incident enlightened us about the importance of developing robust and accurate pedestrian detection method. So while it is important to detect pedestrian robustly, one of the ways to improve the detection performance is inference fusion. So before diving into details of this section, let's talk about the importance of inference fusion. We see the output of detection network is bounding boxes, and the output of a semantic segmentation network is a semantic map. The positive side of detection network is that it can directly classify and localize the pedestrian, while the semantic map can provide only rich features. The downside of detection network is lack of rich features, while semantic segmentation provide poor accuracy, slow, and cannot localize multiple pedestrians. So these two networks can be complement to each other. So what we'll try to do, we'll try to use the maximum feature of each network and fuse the performance to detect a robust pedestrian detection. So now there is a trade-off between fast and accurate semantic segmentation. Conventional image segmentation network like segformer, DDRnet, etc. are accurate, but they are very slow. On the other hand, fast image-to-image translation network like pix-to-pix GAN are very fast, but provide noisy information. So while we are selecting a semantic segmentation network for image segmentation, we need to trade off between runtime and accuracy. So now let's talk about different approaches of fusion-based pedestrian detection. There are two different types of fusion-based approaches for pedestrian detection. First one is end-to-end approaches, where multiple subnetworks are learned together to detect pedestrians. On the other hand, in the modular approach, inferences are fused directly from multiple subnetworks. So subnetworks are trained independently in the modular approach. Now, the example of end-to-end approach are scale-over faster RCNN and SDS RCNN. So, and the challenges in this end-to-end approach is they lack in generalizability while detecting pedestrian, and they are computationally very expensive. And the example of modular approach are faster RCNN using semantic segmentation network and fused DNN. And the challenge in modular approaches are most of the modular approach are complex architecture, and they are also computationally very expensive. In my upcoming slide, I'll try to explain a little more about these different approaches of different methods. So now let's discuss more about end-to-end fusion approach of SDS RCNN network. So SDS RCNN architecture consists of two key stages: a region proposal network, RPN, to generate the candidate bounding boxes and corresponding scores, and a binary classification network, BCN, is used to refine their scores. So in both stages, this SDS RCNN network, authors propose a semantic segmentation infusion layer with the objective of making downstream classification, and which is a substantially easier task. So the segmentation layer infuses semantic feature into shared convolutional layers of each stages. The infusion layer aims to encode the semantic mask into shared feature maps, which naturally serves as strong cues for pedestrian classification. So this is primary overall the architecture of this SDS RCNN network. And the gaps of SDS RCNN network is that when cascading the instances segmentation with faster RCNN, it requires high processing time. And also, SDS RCNN do not have any modular architecture. Everything we need to do in an end-to-end fashion. That is another drawbacks of this SDS RCNN network. Now I'll talk about fused DNN, which is a modular architecture, and it fuses multiple deep neural networks with a soft rejection method to adjust the confidences in the detection results, and optionally uses semantic segmentation network to improve the detection accuracy. So more specifically, this method is a two-stage fusion approach in which initially multiple deep neural networks are fused to generate candidate pedestrian proposal, and followed by an optional semantic segmentation network which rejects false proposal. So, and the gaps of this fused DNN are like fused DNN optionally uses semantic segmentation. So sometimes they miss some important clue information from the semantic map. And fused DNN has a complex architecture, and this complex architecture creates the low runtime efficiency. So these are the downside of this fused DNN architecture. Now, our hypothesis is that we can fuse this output of semantic segmentation and anchor box detection networks to enhance the performance of pedestrian detector. And when we are going to do this, I mean, the challenges that we are facing are listed here. The first challenge is that semantic map cannot separate individual pedestrian locations. And anchor box detection method lack in confidence score due to partial occlusion, different body articulation, etc. And these two different types of networks, these two networks have asymmetric inferences over pedestrian, making the fusion challenging. So, and also parallel processing of multiple networks are required for reducing the impact on runtime efficiency. So these are the challenges. And in our proposed approach, we integrate this pixel-wise semantic segmentation network into the anchor box detection network fusion architecture as a reinforcement to enhance the performance of the pedestrian detector. And this will be achieved by introducing a pixel-wise consensus-based approach. So this is something that we are proposing, a pixel-wise consensus-based approach for fusing different inferences of two different or multiple different asymmetric network. So now I'll talk about details of our proposed solution. So here is the high-level architecture of our proposed solution. To overcome the challenges that I mentioned earlier, we propose a solution where we infer pedestrian from an object detector and a semantic map. Then the inferences of both networks are fused based on the consensus. Finally, inference fusion architecture provides a joint. Finally, inference fusion architecture provides a joint prediction. Let's see the details architecture. An input image is fed into the object detection branch and semantic segmentation branch simultaneously. The output of semantic map is masked for pedestrian instances and mapped into the detective bounding boxes from the object detection network. The inferences of both networks are fused based on the consensus on detected pedestrian. So here, this is the main inference fusion architecture. So the output of the object detection branch is the bounding box scores and location, while the output of semantic segmentation is a semantic map. So by using appropriate color thresholding, pedestrian instances are masked from the semantic map and converted to a grayscale image. Then we calculated the number of overlapping pixels of pedestrian mask with the bounding boxes. After that, we use a scoring function to calculate the updated detection confidence score. So this is our inference fusion architecture. So as we use two different branch, one is object detection branch and another was semantic segmentation branch, we can use any of the single stage or two stage object detection branch, object detection network for our object detection branch. We can use any of the object detection network for our object detection branch. So here's an example of bounding box detector branch. We can use SSD as a bounding box detector or any other two-stage detector. For example, this single stage detector has input layer followed by some convolutional layer for feature extraction and then SSD layer for bounding box localization. Finally, a non-maximum suppression trace is used that helps to remove the redundant bounding boxes on the same pedestrians. So this is the architecture of sample single stage network. Single stage object detection network. So now for another branch, semantic segmentation branch, we can use any of the conventional semantic segmentation. For example, we can use segformer. So segformer framework consists of two main modules: a hierarchical transformer encoders to extract coarse and fine features, and a lightweight all multi-level perception decoder to directly fuse these multi-level features and predict the semantic segmentation mask. If we go through the architecture in details, like an input image of length and width of H and W is fed into the network, and then divide it into small patches of size 4x4. Then use these patches as input to the hierarchical transformer encoder to obtain multi-level features at different image resolution of 1x4, 1x8, 1x16, and 1x32 compared to the original image size. Then pass these multi-level features to the all MLP decoder to predict the segmentation mask at a H by 4 into W by 4 and number of class resolution, where NCLS is the actually number of categories or number of class in the semantic map. Now let's discuss about another semantic segmentation branch, which is a fast network that I earlier mentioned. We can use pix-to-pix GAN, which is a fast semantic segmentation network. So for pix-to-pix GAN, in the training stage, semantic image X are used, which are conditioned by a colored RGB image C. And during the testing phase, to generate a semantic map, the pix-to-pix GAN takes the color RGB image X as an input condition, and then uses a conditional GAN to generate the semantic map. Now we have semantic segmentation result and bounding box detection result from two different branches. So to calculate the joint confidence score, we utilize pixel level information from two deep neural networks models. If A be the total number of pixels within the bounding box of detector, and N be the number of pixels within the mask as shown in the figure. And we first compute the amount of non-overlap pixel between two inferences, which can be denoted by M, such that M equals to A minus N. So we then compute the joint confidence score using this using our scoring function. The scoring function has two different weights for overlapping pixel and non-overlapping pixel. So the weights for non-overlapping pixel are same as the confidence score of the detection branch, and weights for overlapping pixel are 1/1 minus p. So that means basically we boosted the confidence score on the overlapping pixel, so that our model can provide boosted confidence when there are overlapped pixel between two network output, like semantic segmentation and bounding box network output. If there are overlap, then our model can provide the boosted output. Now let's take some boundary condition of fusion algorithm. So if p equals to 1, I mean probability equals to 1, that means model is detector network is fully confident about the pedestrian, 100% confidence, or n equals to 0, that means there are no overlapping pixel, then the model relies only on the confidence score of the detection network only. So these are the two special cases when the model don't take any information from the semantic segmentation network. So otherwise, the method computes the weighted average of number of overlap pixel n and the number of non-overlap pixel m. So this method considered the number of overlapping pixel n with much higher weight, which is 1/1 minus p. So while boosting the confidence score, we make sure that the confidence score does not exceed 1, and we ensure this by using a clipping function in our scoring mechanism. So here is the pseudocode of our fusion algorithm. The object detection branch provides the bounding box says with confidence of, for example, here 0.45, and semantic segmentation provide the pixel level information, and then applying the scoring function on overlap pixel, the fusion algorithm provides a boosted confidence score of 0.90. So this way we just improve the confidence score. Now I'll talk about our experimental result. So, and the experimental setup. We benchmark our result on a 64-bit Ubuntu server, which has a 64 GB memory and 2 NVIDIA GPUs. To evaluate our results, we use a 60% public dataset, which contains 2,975 training images and 400 test images. To show the generalizability of our method, we created a Greensboro downtown dataset. So as I mentioned earlier, we performed a cross-data evaluation to assess the generalizability of the developed framework. Cross-data evaluation is training. We applied the cross-data evaluation method. So cross-data evaluation is basically training on one dataset and testing on another dataset. It is not the same dataset has two different subsets like training and tested. It's totally different dataset. So since we use a pedestrian detector and a semantic segmentation network to predict pedestrian jointly, a parallel implementation of inference fusion speeds up the runtime of the overall pedestrian detection system. For this purpose, our inference fusion method is implemented using a multiprocessing approach for detecting pedestrian concurrently. In one process, we implement the pedestrian detection branch, while in another process, we implement the pedestrian mass segmentation branch. So each of these processes is implemented using a separate Docker container and a discrete GPU. We, however, use the shared memory to fuse the output of these branches. And we make sure that we are using a timestamp to make sure that the frame are synchronized. So we thoroughly evaluated and compared our method against state-of-the-art pedestrian detection method. Our validation experiments include the fusion of 8 object detectors and 4 semantic segmentation network, overall 32 fusion models. So for benchmarking purpose, we use two parameter like average precision and miss rate. AP is denoted for average precision and MR is for miss rate. And we know that average precision, the higher is better for a model. If model can provide high average precision, that means the model performance is considered as better. And also the lower the miss rate, it is better. And here in the table, I use the row wise, all of them are the 8 row representing each detector network, and the column wise, I provide the semantic segmentation network. And the first column is basically the baseline column. That means there was no fusion performance here. But then each column basically represent the semantic segmentation network. And if we stand in any of the point, for example, 56.99 average precision, that means it represents the fusion between CSP and this segformer. So now we can observe that the performance of pedestrian detection is notably improved when fused with a pedestrian mass segmentation network using the proposed fusion inference method. For example, RetinaNet fused with segformer increases the AP from 34.84 to 42.38 and decrease the miss rate from 65.15 to 57.61 on CT% dataset. And SSD mobile net fused with FCHRD net increased the average precision from 46.30 to 74.56 and decreased the miss rate from 53.69 to 25.43 on Greensboro dataset. So we see for each fusion cases, our model improved the detection performance compared to the baseline network parameter. Now, detection comparison. The top row represents the input images. Then the middle row indicates the corresponding semantic map of input images. And finally, the bottom row shows the ground truth of baseline detection and the detection with the fusion mechanism. Green color bounding boxes represent ground truth. Blue color bounding box represent baseline detection. And red color bounding box represent improvement with fusion method. So these are some graphical or pictorial evidence of our detection method and the improvement after applying this fusion mechanism. Due to the parallel utilization of 2 different networks, we also achieve competitive runtime efficiency from our fused models. In fact, the overall computation time of the proposed fusion framework is almost the maximum of the computation time of the slower branch. For example, SSD MobileNet has detection time of 0.011 second, and Pix-to-Pix GAN has processing time of 0.011 second. And after fusing these 2 methods, the framework exhibits 0.012 second processing time, which is negligibly high, or which is the difference is very minor after applying this fission technique. So here is a video demonstration of our method. So although there are noisy information from the semantic map, the fission framework improved the detection performance. And red color bounding box represent the fission result with after improvement. So now this is the I came to the conclusion of my presentation. So in conclusion, we implement a pixel-wise consensus-based approach for fusing inferences of to asymmetric network. We create a pedestrian dataset with 1746 annotation of 867 images, and we named the dataset as Greensboro Downtown dataset. And extensive validation experiments are carried out, including the fusion of 8 object detectors and 4 semantic segmentation network. Overall, 32 fusion models. So, these 32 fusion models are applied in 2 different datasets. So in total, we showed the result of 64 different models. Now I'll try to answer if you have any questions.
Much. Any question now to Mashuk?
Yeah, Mashuk, you mentioned you have a hypothesis. I was looking for you to tell me that since you have an hypothesis, you're going to say that, okay, what happened?
Yeah, when I showed the experimental result, I think my hypothesis.
What is that experimental result is telling me? That you are satisfying the hypothesis?
Yes, Professor. The experimental results show that, okay, there are significant improvement after fusing, and we were successfully able to take the inferences of semantic segmentation and fuse this information with object detection network information and improve the overall detection performance.
Okay, can we go back to your hypothesis?
Okay,
What was your hypothesis?
Yeah, please, our hypothesis. So here is our hypothesis, Professor.
So what kind of test are you applying to prove your hypothesis? And then, by the way, your hypothesis, you have to put your hypothesis as a question, isn't it?
Yeah, the sort of claim.
Yes.
Yeah, but then what kind of hypothesis, I mean, what kind of tests are you running to say that, okay, now what I said, it is true?
Professor, when we benchmark our result, and in our experiment result, we can see that our results show the performance improvement compared to the state-of-the-art model. So we can say that our hypothesis is true. it's not.
Are you saying that, okay, what kind of test are you running to say that your hypothesis is true? Are you going to be running some significant test or chi-square test, t-test, what test?
Yeah, this is one of the way to justify this. I understand, Professor, your question, but we justify this in some other way, like cross validation. We test our model in different data set, and based on this testing on different data set, we came to the point that okay, our hypothesis is acceptable.
No, I have a problem. Hold on, Islam. I have a okay. I could have put their objective. Your objective is this. But when you say hypothesis, it means that you're going to prove your hypothesis. There is no but and if.
I'm not understanding, Dr. Mohamed.
When somebody puts in a hypothesis, they have to prove the hypothesis, whether the hypothesis is right or wrong.
You can verify. There are different ways that you can verify a hypothesis, and he has verified his hypothesis via verification. Via benchmarking. That is true, but you might have other approaches of doing that. But are you mentioning that you cannot verify a hypothesis using experimental results and extensive benchmarking? That's okay, but I think we can verify this hypothesis conducting the experimental benchmarking that he has done here. So are you mentioning that you cannot verify a hypothesis experimentally?
Okay, how much experimentally we are doing? First of all, we are doing. This is what he's doing. It is. Are you doing a simulation, or you doing? This is a real test now.
It's a real test on real publicly available data set.
64 models. 64 models. No, it is not called simulation. 64 models have been developed, and over three real data sets, they have been validated.
Yep.
Did I miss this information, Dr. Karimuddini?
Yeah, I think he did provide. Can you go to the
I'm sorry, because a guest came in unannounced, and so I missed your beginning. But the reason I am asking this kind of question, because I know at some point soon you're going to be defending these things. Okay.
Oh, Matthew, go ahead and explain the experimental results and the significance of your experimental results.
Okay. In this slide, actually, there are two. We have two tables. Data set. The top one is on the city person data set, and if I'm going to explain the top table first. Here, the model is
provide the big picture, because as soon as you go through the details, you are missing the big picture. First, provide the big picture first. Don't go through the details of the results. First, tell what this slide is saying about.
Okay, this slide is saying about the improvement of detection performance after applying the fusion mechanism on city person and Greensboro dataset. So the top table showing the result on city person dataset, and we benchmark our result on two parameters like average precision and miss rate, and we see that for each and every cases when we apply the fusion mechanism, our fusion mechanism improve the detection performance for each and every network when we apply this fusion mechanism.
Where is that 32 models that I'm discussing, or 64 models?
Now, the 32 model, if we look at the row-wise, we put all the detector model, and column-wise, we put first one is without fusion result. That's why we named it as baseline network. And for other cases, I mean, for each semantic segmentation network, we provide in the column-wise. The seg format, DDRnet, FC, HRnet, piece-to-piece GAN, all are the semantic segmentation network. So, and each value here that provides, for example, I highlighted with red color bounding boxes, the RetinaNet 1, when the RetinaNet is fused with segformer, it showed the average precision of 42.38, whereas the baseline network, that means when RetinaNet performed without any fusion mechanism with any semantic segmentation network, its average precision was 34.84. And after applying this fusion mechanism with segformer, we see it increased from 34.84 to 42.38. And also the miss rate, which was 65.15, that decreases to 57.61. So this table basically shows this our the detection result of our fusion mechanism. And the bottom table shows the result on Greensboro dataset. And we mention it as a cross validation because the model was trained on different dataset and then test on another dataset. So as our model can perform a completely new dataset and shows the improvement of detection performance, so we can say that our model show the generalizability and ability to perform in new dataset, and this is called cross validation. So this way we justified our hypothesis. I mean, is that somehow answer, Professor, your question?
Right. Let me ask another question.
Yes, Professor.
Since your average precision is under 70, okay, for the best one that you are showing it in here, is this something that you can live with?
For example, it's a trade-off. Average precision is 90.74, Professor. If you look at here, cascade mask RCNN with and segformer, the first column, it shows the average precision of 90.74 on Greensboro dataset. So it varies on the different scenario.
Let's hear the question first.
Yeah, answer the question, Islam.
Okay, Professor.
The question is, your average precision is under 70%.
Mm-hmm.
Can you live with?
Can he what?
Can you, is it something satisfactory for the application that you're looking for?
I don't think that's wait, Mashuk. I don't think that's a question to Mashuk, and it is not average position average precision of Mashuk. So it is not AP from Mashuk. It is a base network, and remember, these are state-of-the-art networks, right? So for example, mask RCN and so on, they are state-of-the-art sort of networks that you can see here. And despite the fact, so the AP is not just saying that it's good. The data set is very complex. CT%, those who are working in this AV domain, they are aware that CT% is one of the most complex networks that you do have. That's one. Second, it is not mesh this 65.94%. It is not Mashuk performance, AP performance, right, or MR performance. What is Mashuk performance is that improving from 60.5% to, for example, 67.49% when he fused it with segformer, right? So the improvements are the work that Mashuk have been doing, right? So, and then if you look at here, the art of his work is not that he's improving, for example, one of the state-of-the-art mask RCN and then improve it to 67% or whatever. Especially his work is significant when the performance of the object detector is relatively lower. If you look at the bottom row, for example, 34%, right? And then he fused it, so a lower end network, for example, SSC or let's say RetinaNet or whatever, which are less computationally expensive, and then he fused them with kind of semantic segmentation, then you see a significant boost there. So it's quite nice that you are using a low-end network rather than quite complex computationally expensive network, and then you improve and boost the performance over there. So the base ones is not Mashuk's one. The improvements are Mashuk's claim here.
I understand he's comparing his result with the baseline. But the question is going to come, are we looking improvement over the baseline, or we are looking improvement over the application that I can use?
And remember, the other thing that I forgot to mention is that in autonomous vehicle kind of works, you are not looking at individual frames, right? So you typically you have different frames, and then you are even if in one frame you are missing, you are going to catch it that in the other frame, right? So it is not that if you are 65% and you miss a pedestrian, that's the end of the world and you're going to hit the pedestrian. No, that's not the case. In the next frame, or when you get closer, right? So a lot of these pedestrians are far away, and that's the difficulty of city percent. And if you look at this city percent is one of the most challenging data sets, and people have shown the results all is competing with each other and improving. Okay, I came up with a better network, and here is my results, and so on and so forth, right? So and these are not Mashuk's results, right? So on the baseline, these are not Mashuk's results. So and still you can see that he's able to provide improvement, right? So so make it short. Mashuk's claim is not on the baseline; it's on the improvement. So if the baseline is poor, that's not Mashuk's problem. That's the state of the art sort of networks, plus the difficulty of the data sets that you can see. That's first. Second, in the autonomous vehicle applications, you are not judging things based on the individual frame. However, for assessment of your results, you have to deal with the individual frames that you are assessing. Hopefully, this addresses your question.
So this average precision, all this result that you are reporting, is it over the whole entire mission, where the mission that I define as going from A to B?
It is not exactly, Professor, the way you're thinking is a particular for mission, because it's a standard publicly available data set. And we cannot come, the way you are thinking is a mission, it's totally different. When you apply for a mission, in different mission, different scenario, we'll have different challenge. So it's not like
Is there a snapshot over a particular time?
For example, if we
no time is snapped. There are no time is snapped. So they are mix of, some of them might be kind of successive images, but not all of them. And then there are data sets and it's not from A to B going to one track, right? So it's a mix of some of them successive image, successive phrase, some are not, and that's the way.
Yeah.
But that's one of the most referred data sets in AV domain.
Yeah, and Professor, if you want to show some example, like we tested with our model in the parking lot, there are 3 for pedestrian, and from spot A to B, there is a mission. If we set like this, and only for 3 for pedestrian, our model can detect 100%. But this is not something that result we can present for small. But we present our result on a publicly available challenging data set that Professor Ali already mentioned, and there are so many mission. On this data set, they have so many segment of mission you can consider. This is not only single mission. There are so many segment on this data set. For example, in city person, they have almost in different city, not only on one city. In Europe, they have almost 20 cities, 20 different cities, the data set. And in 20 different cities, there are different segment at different time. So there are the summary is that it's a really challenging data set. So different kind of mission are added there. So it's not a single mission, Professor.
I'm sorry, maybe I'm a little bit ignorant. Imagine that you're going from your lab, Dr. Karimuddin's lab in Martin's building to courthouse.
Mm-hmm.
Is that the kind, okay, when you say city of Greensboro, what does that mean? Meaning that somebody is going from the Martin's building to downtown Greensboro. Is that what you're saying, or what? What does these things mean when you say city Greensboro?
They have picture. They have drive the car in Greensboro, I think particularly in downtown, and they have collected different instances of especially those that there have been pedestrians there. and they have collected individual image frame and annotated and use it as a sort of data set. So they are not time-stamped sort of kind of successive image. No, they have been mix of frames that they have captured across the city.
So in here, what is important? You're saying that detecting pedestrian regardless of the order. Yes?
No, Professor. There's for example, one sequence, if there are pedestrian, as long as there are pedestrian, we collect this sequence. And maybe therefore in some, for example, after driving 10 more minutes, we'll see another sequence of pedestrian, we collect all the pedestrian. Because if there are no pedestrian on a video frame, we just skip this video frame. So this way we collected, as long as there are, I mean, yeah, there are sequence. I mean, if you think about the pedestrians are sequential, we did not drop any pedestrian when they are in a sequential frame.
Imagine you going from Martin again to downtown.
Okay.
And along the way, you see you see a lot of people in the left, in your left or in your left, let's say that.
Okay.
In your right. So you are, regardless of the time, when you're going from A to B, you're going to be collecting all the information regarding pedestrian in your way to the destination, for example, or within the 10-minute period that you are driving.
Yeah, we collected all the pedestrian when you see the pedestrian.
Okay. And then within what you are trying to do is you are trying to see whether your technique can detect this, whether it is crowded or less dense and all this, right?
Right.
Okay. So that is okay. Okay. And then the column one, it is your method, right? Your
No, column one is baseline. Oops.
the column one is what?
Baseline method. Without any fusion performance.
Column one is not no fusion.
Oh, columns are no.
Column one is no fusion.
No, okay. Except the baseline that you said, you have second column, third column, fourth column, and fifth column. Those are your method, right?
Yes, Professor.
Okay. All right. Okay. I'm sorry that I took so much time.
No, actually, it was helpful. And then coming back to your point, Dr. Homifer, I understand the hypothesis might have been referred in different contexts, different way. And I see another comment from Biniam there too that is suggesting using, for example, hypothesis instead of objective. Informal methods hypothesis has a different meaning, maybe in another context that you are referring. Whatever hypothesis he had led me to see initially when he has a research question and he had a thought that saying that okay, this fusion might improve the performance, and he called it hypothesis, and then throughout these experiments he did prove it. So if you think that it is not a right terminology that he has been using, that's fine. He's going to be changing it, but that was his way of explaining it. He was initially, before even running the experiments, he was under this he was thinking that okay, this fusion might improve the performance. He called it hypothesis, and then he later proved it. So it wasn't objective, it was a thought that was saying that okay, this will happen, and it was happened. Okay. I understand always you are suggesting that okay, do significant analysis or those sort of things. I think Meshuk is going to be good to do so and say, especially here on this, how much improvement you're going to get after all these fusions, if you can.
Okay.
And and Benjamin always offered help to make that significant analysis conducted here, if you can.
Let me ask one more question. This is you have anchor base and anchor free. There are two methods, right? So you're using anchor base, right?
Yes, yeah, most of the baseline method are
How
anchor.
come you didn't look anchor free?
The anchor is the whole framework is based on the fact that there is an anchor, and then based on that, he then overlay the semantic segmentation into that anchor, and is saying that, okay, now how much consensus we do have between these two, right? So that's the whole framework. So it is not, this method is not applicable to anchor-free base object detectors.
Yeah, but what I'm asking, Mashuk, is you can also do with anchor free as well. How come you didn't do it?
Yeah,
This method.
in result is bounding box, it doesn't matter. If in result is bounding box, we can also apply to anchor free method. This anchor free method, eventually anchor free object detection method give us the bounding box as well.
But one of the big problem with anchor base is how do you lay out the anchors in your space? Remember that the only thing that you have is you say that, okay, I'd like to have this many number of anchors here and there. But how do you know that that anchors that you are laying in top of your data is good enough? That's why most of the time people now are looking at anchor free rather than
Actually,
anchor.
Professor, it's an arguable debate. For example, in YOLO, in the initial version, they didn't use YOLO 1 was anchor free. Then they applied YOLO 2, they bring the anchor box again. So it's a kind of arguable thing. Sometimes some researchers say that, okay, anchor based are not good. We develop very good performance with anchor free, but on the next day some other researchers work on it and they said that, no, we have good performance on the anchor based. So, and because they designed their anchor box, for example, initially there was some search algorithm to find these anchor boxes. Then without using the search algorithm, SSD brings something like they use some default bounding boxes to create generate some anchor boxes. So it's the arguable issues, and I'm not focusing on this task particularly, but my inference fusion or consensus based inference fusion can improve the detection performance if any of the network can give me the bounding box end results. So I rely on the end result of the bounding box. So it's a still debate. So I'm not focusing there, but my focus is little different from there.
Okay, thank you.
No problem.
Yeah, it's a very interesting problem that you're addressing.
Can you hear me?
Sure.
Yeah, hello.
Yes, we can hear you.
Yeah.
Rolf, you're trying to say something? Yeah, we can hear you.
Yeah. Thanks for the presentation. So my concern that I have is about the robustness analysis of your network. Do you sort of try adding some noise to the images to see how robust the trained network would be to the disturbances into your text data set?
This is not something like we're not designing any filtering or this kind of robustness. Here, robustness is that how good our model is performing, and it's already there are so many noises in our. For example, the dataset is really challenging, so we need not to add extra noises there. Some pedestrian is really difficult to even in 60% dataset. There are some pedestrian is really difficult to see. I mean, in your, I mean, if it is not annotated earlier, some human person cannot, maybe some human person can say that it is pedestrian because it is too tiny, so tiny that it's really difficult to see. So in this system, I mean, the way you are thinking that adding the noises and tell that the model is robust or not, because it's not, our model is not detecting 100% accurately. So we need to add something like adding noises and see how model is performing, something like that. We are not testing in this way. I don't know you understand. I mean, it is clear to you, or it's somehow it's answered your question.
Yeah, it answered my question. And one other thing is, I'm kind of
sure.
is it sort of doing a real-time prediction?
Yeah, it's a real time because I show you the runtime efficiency. So when we see the runtime efficiency, so you know, if for example, Waymo car, they are using a LiDAR, and their LiDAR scan frequency is 10 Hz. That means they can scan 10 frames in each second. So they are claiming that their Waymo car is detecting pedestrian and other object in real time. So here, if you see our runtime efficiency, for example, after combining pix-to-pix GAN and SSD, our frame is almost close to 90 frame per second. So SSD mobile net and pix-to-pix. But other than this, most of the network will work as runtime, like faster RCNN, even faster RCNN, SSD mobile net, and SSD mobile net FPN. So all of them, most of them are working in real time.
All right. Thank you very much.
No problem. Thank you so much for your question.
Yeah, I have one question.
Sure.
Yeah, thank you for the presentation. Yeah, very interesting. So yeah, I have one quick question is, so you train on 1746 data sets, right?
No, I use most of the pre-trained model.
No, I mean training data.
Training data, we created on, which data set? For example, most of the model are trained on CT% data set. CT% has around 3,000, 3,000 images.
Did you like mix those data and then use those as a training, or use like Greensboro and the other data separately?
I didn't hear you clearly, but you mentioned that should I try to mix the data set and train?
Yeah.
Train?
Yeah,
we can do this. We can do this, but as this model are trained on a very huge data set, trained on GPU for a long time, I'm not sure it will give us any more improvement. But yeah, we can do this. And in some of my other work, I created my own data set. I train it from the scratch, and yeah, on this particular, my data set, it works well, but it don't work well in some other data set. But yeah, yes, CT% is a robust data set and very challenging data set, and compared to CT% dataset, my Greensboro dataset is, and I'm not saying that it's not very challenging compared to that dataset. It's a small dataset, so we can assume that if we train it, maybe it will not perform. The performance will not be improved that much because it's already performing. The CT% dataset is already robust enough. But yeah, if we try some other dataset like huge size like CT% dataset, there might be a slightly improvement on that particular dataset. But on cross dataset evaluation, I'm not sure how much it will improvement. But yeah, on a particular, because it already know the environment on the same dataset, it will improve a little bit on this dataset. Like if we test it on Greensboro dataset, and before testing on Greensboro dataset, if we trained with mixed dataset like CT% and Greensboro, it might give us some improvement on Greensboro dataset.
Okay. Yeah. Thank you.
Yeah. Thank you so much for your question. And in addition, I would like to say one more thing. That's okay. If we trained a model, for example, in New York data set, New York is a very clumsy environment, and you will see a lot of pedestrian, different challenging scenario. If we train a model on a data set like New York and test with the same model in Greensboro, we can say, yeah, the performance will be very good, and it will be able to, we expect that it will be able to detect pedestrian in Greensboro data set significantly or comparatively very well. But if we trained a model on a data set like similar to Greensboro area and try to use this model to detect something in New York, it might not work because this scenario is totally different and more complex. So this is the way, the things are working.
Yeah, one more question. So how do you annotate this data? Like, is there
That's another good question. I annotate this manually. Like there is some software for annotation, like image level soft. We can use this. So far people are using this kind of software, but there are some way to automatically label your data set. I talked with one of the person who is the creator of JAD dataset. JAD is one of the most popular dataset for pedestrian tracking, and his guy's name is Dr. Amir Rasoli. He's now a professor in Canadian University, and he, in one of the conference, he mentioned that they are also trying to annotate data automatically with some software, but still people are not rely on this software because the accuracy of this kind of software are only 40%. Still, they need to cross-check with manually the level information. So yeah, there are some, yeah, so some people are also working on automatically labeling this data set, but still people, the best way to label the data set is the manual way.
Mhm. And then how do you validate those manual data sets? Like just, let's say you annotated those data, right? Yeah, how we
When
can
a human
validate
is
it.
annotated, there is no way to validate after that, because human, we should have to believe. Maybe you can check with multiple person. That's the thing that we can do, but there is no other way to validate the ground truth data.
Yeah, that's what I'm asking. Yeah. Okay. Yeah. Thank you. That's good work.
Thank you so much.
Yeah. Any other question? That was a very wonderful conversation. One announcement. Thank you, Mashuk. Just one announcement. I'll put a survey in the chat box. A group within NC-CAV is conducting a survey on the opinion on understanding of the CAV infrastructure requirement and needs for public transportation. I did put it in the chat box. It shouldn't take you more than 10 to 15 minutes. Most people in this talk are have some familiarity with the concepts of CAVs, and hopefully you can spend 10 to 15 minutes to provide your feedback on this survey. So I did put it in the chat box. If you can, please help with that. That would be appreciated. Thank you everybody again. Dr.